Okay, I guess maybe we can start. So hello everyone, welcome to 130B, quantum mechanics. So today we are continuing to discuss quantum many-body states, in particular quantum many-body systems made of identical particles. So let's first recap what we have learned last time. So first of all, when we want to describe a many-body system, put a lot of particles together, the key tools that we use is this tensor product. This tensor product allows us to combine many small vectors which describe the single particle state together and then combine them into a many-body state. So for example, in this expression, every state vector here is a state vector in the single particle Hilbert space, which maybe you can consider it as a d-dimensional vector. By combining them with tensor product, you basically obtain d to the nth power. If there are n of them, then d to the nth power very long vectors, that is a state vector describing the many-body state. So this notation basically means that the first particle is in alpha 1 state, second particle is in alpha 2 state, and the last particle is in alpha n state. In such a description, all this sequence basically describe the state of each particle. And we know we can use this kind of a basis to describe many-body states if and only if the particles are distinguishable. You can label them. What is the first one? What is the second one? So this becomes a problem when we want to discuss identical particles. Identical particle does not admit a labeling. So the first particle in alpha 1, second particle in alpha 2, or the other way around, they basically correspond to the same state, or they should be described as the same state. Or more precisely, we can think identical particle is a property of the physical system, is a symmetry of the physical system. By saying that the system is made of identical particles, we mean that if you arbitrarily exchange any pair of particles, the property doesn't change. The property of the system doesn't change. It doesn't make any difference. So for example, if you can consider any physical observable of the system, it should not be affected. For example, its expectation value should not be affected if you exchange two particles. By exchanging two particles, you can simply exchange the labels that label the state of these two particles. That's also equivalent. So if you do any permutation on these state labels or this sequence, then by requiring that the system is identical, made of identical particle, we basically mean that any physical property is not going to change, expectation value not going to change, variance also not going to change, any statistical feature is not going to change. So fundamentally what that means is basically the probability distribution is not going to change if we exchange two particles. However, in quantum mechanics, we don't describe probability distribution directly. Instead, we use a wave function or a state vector to describe it. So we know that state vector or the component of the state vector is the square root of the probability distribution. So if the probability distribution is not changing, that basically means that the state vector under exchange, you basically like take a square root. They should be equal up to a phase vector. And then this phase vector, we further consider that because exchange is a second order process, that if you do it twice, it goes back to itself. So this phase vector can only be 1 or minus 1. So that leads to two different types of identical particle systems. One is called boson systems or bosonic systems or fermionic systems made of bosons or fermions. For boson, their many-body wave function has this property that if you arbitrarily exchange two bosons, the wave function doesn't change. But for fermions, if you exchange two particles, two fermions, then the state vector or the wave function acquires a minus sign. So that's the exchange statistics or the exchange sign of the fermion, sometimes also called fermion sign. So that leads to this idea that we can actually define symmetrization or anti-symmetrization operators that takes any state in this many-body basis and then convert it into a basis which either satisfies this bosonic property or the fermionic property. For example, any state after symmetrization will automatically become invariant. The basis will become invariant under permutation of the labels. Example is like this. If you take this alpha beta state and symmetrize, then it will be invariant. But if you take it anti-symmetrize, it will end up with a new basis state or a new state. You can use that as a basis later, but it will give you a new state which has this fermionic property that exchange leads to a minus sign. Okay? So we can construct these bosonic and fermionic states using symmetrization and anti-symmetrization. And then this anti-symmetrization also explains automatically the Pauli exclusion principle that if you have two particles occupying the same state, under anti-symmetrization, that state just vanishes. So that means there's no such a fermion state which can have two particles, two identical fermions occupying the same state simultaneously. This state actually includes position quantum number and spin quantum number. That means at the same position in the same spin mode, you can't have more than two fermions. But if you forget about the spin quantum number, actually at the same position, maybe you can have spin up and spin down two fermions still as well. Okay? So now let's do a counting of how many states are there in this many-body Hilbert space. So at the very beginning, we start by constructing the full many-body Hilbert space of distinct particles. Because they are distinct, then each particle can assume one of these d different possible states. And then if you have n particles, then there are d to the power n distinct states. So d to the power n, that's a very big state space, has so many states. But then we want to count how many states within this big Hilbert space. There are two subsets. Actually, they have a small overlap. One subset is a bosonic state, the other subset is a fermionic state, and then we'll try to count the number of them. So the number of fermionic states or basis states in this subspace can be counted because fermions, so we basically have each particle can have d states, and there are altogether n particles. So that's the setup. So for fermions, let's talk about fermion first. You have n particle, meaning that you have n different slots. So this 1, 2, and so on to n slots. And then you want to occupy these slots with particles. Actually, all the way to D. The slots are the states. So we want to occupy the states with particles. So we have n particles like n little balls. And then you want to put these balls in these boxes. And then the rule is that either this box or this slot contains no particle, or it contains one particle, but it cannot contain more than one particle because they are fermions. They have Pauli exclusion principle. So you need to put these, for example, put it here. You need to put n different balls in d different slots. So such a state basically describes that there is one fermion occupying the first state, one fermion occupying the second single particle state, and then one fermion occupies this particular single particle state. And the remaining states, single particle states, are not occupied by fermion. So it basically describes three fermions, which are in state 1, 2, and this one. Okay? So how many different ways to put n different n little balls in these d different boxes? That is the combination number. That is d choose n, right? So d choose n is basically d factorial, n factorial, d minus n factorial. So that's why the number of fermionic states basically goes like this. So this is what we define as the Hilbert space dimension of the fermions. And what about the bosons? The situation of boson is a bit different because for bosons, you can put more than one balls in the boxes. So there's a trick to count the number of possible combinations is to introduce a stick or a divider between these balls. Because for n bosons, if you want to partition them into d different parts, that's the idea. So for example, you have n bosons. Let's say 5 bosons, you want to partition them into 3 different parts. Then that means you need to insert like 2 dividers. These dividers can either be inserted all in the front then that means the first state is not occupied by any boson. Second state, not first state, second state, and the third state. And the third state occupied by 5 bosons, for example. And you can also move this bar to anywhere. Then that basically means that the first state is not occupied by bosons, second state occupied by 3 bosons, and the last state occupied by 2 bosons, for example. So in this example, we have n equals 5 bosons, and then we want to partition them into d equals 3 different parts, such that it describes the situation that we have 3 possible single particle states for the boson to occupy. And in the end, we found that these 5 bosons occupy these 3 single particle states in such a pattern. And the goal is to count how many patterns, how many possible patterns are there. So in order to count these patterns, you can see what basically happens is that the slots, you can treat this stick or this divider and the ball both as an object which can fill in these slots. And the total number of slots you have here is basically n plus d minus 1. Because d minus 1 is the number of dividers you need to put between the balls in order to separate the ball into d different parts, right? And then you can put the dividers anywhere, and then that basically means that you need to choose where to put the divider, because once you put the divider, decide the place of the divider, the remaining slots will automatically be occupied by these balls, by these bosons, and then that creates a pattern, right? That creates a legitimate configuration. So then you basically need to choose where the dividers are. Or alternatively, you can say you want to choose where the balls are. That's the same combination number, and that number is given by there. It's n plus d minus 1 factorial, and then n factorial. So that's the number of boson Hilbert space. So this is the combinatorial problems that you use these ideas. You can count how many bosonic states are there in the many-body Hilbert space and how many fermionic states are there. So this d to the power n is the total number, the total dimension of the Hilbert space, and there's a bosonic subspace of this dimension, and there's a fermionic subspace of the other dimension. It turns out that if you substitute a specific number into this equation, let's say, for example, if we consider the case n equals 2, d equals 2, that means this is like a single qubit. Every particle can take can be either 0 or 1, can take 2 states, and there are only 2 of these particles. So how many symmetric states we can have? We already know if you have 2 qubits, then the symmetric state corresponds to the bosonic state corresponds to the triplet state, right? And then the fermionic state or the anti-symmetric state corresponds to the singlet state. By the name, we know there are 3 states, there's 1 state. And you can check that the formula works, because when n and d are both 2, then this is 3 factorial over 2 factorial, basically. So that is 3. And then this guy is 2 factorial over 2 factorial, which is 1. Okay? So this is 3, this is 1, that is satisfied this counting. So in this case, d to the power n itself, the total Hilbert space, has 4 states, and then 3 of them are symmetric states, and 1 of them is an anti-symmetric state. And then if you sum these 2 numbers together, that spans the full space. That means the full Hilbert space can be nicely partitioned into symmetric subspace and anti-symmetric subspace, or fermionic subspace and bosonic or fermionic subspace. But this is not generally the case. This is only the very special case with d equals 2, n equals 2. If you try a larger d or a larger n, you can try it. I don't want to show it here. You can do this calculation, and then you will find that in general, for larger n and d, very generally, these 2 numbers add together is only less equal than d. It's not always equal to d, which means that these 2 subspaces only occupy really a subspace. It's only occupy a part of the Hilbert space. So inside the Hilbert space, there are states which is falling in this subset, which correspond to a bosonic state. There are also states that are fermionic, but there are also states which is outside both subsets, and those states doesn't describe identical particles. Those states are not legal, basically, for identical particle. If you can label this particle, those states are legitimate many-body states of distinct particles, but those states are not legitimate states of identical particles. So identical particle occupies a smaller subspace than what we previously think of. So this the full Hilbert space basically is what we call the first quantization many-body Hilbert space. And then within that space, there are the subspace which describe identical particles. So in principle, if you want to describe like a quantum state of identical particle, you can take out those states in this subspace and try to combine them and superposition them linearly, and that creates quantum states, for example, that describes bosons. But this is not a very convenient approach because we need to keep in mind every time when we do a calculation, we have to always consider whether our state vector or the wave function is symmetric or anti-symmetric. We need to always ensure that condition in order for it to be either a bosonic state or fermionic state. But so it's not that convenient because we hope that in general we should be able to linearly combine any state in our Hilbert space. But if you try to combine any state in our Hilbert space, you will end up with a too large space, which actually contains illegal states. So the question here is there a better way to organize this many-body Hilbert space that only focus on these legitimate physical states of either bosons or fermions? So, of course, you will tell me whether you want to consider a bosonic system or a fermionic system. And once you tell me I want to consider a bosonic system, okay, I can pick out this subspace for you. I can have a construction of the basis in such a bosonic state that automatically satisfy the symmetric property that does, and then you are free to combine all these basis states as you wish, and then you never get illegal state out of this subspace. So the idea is try to understand what are the basis states in this subspace in order to construct many-body states in a more convenient way. Okay, so that is the goal, and those states, those basis states in this space are called the Fock states. And then the corresponding space are called Fock space. So this is a bosonic Fock space, and then this is a fermionic Fock space. In many cases, the reason that in the original language we create a Hilbert space that's too large and describe many redundant illegal states is because we use an inappropriate language to describe the many-body system. In many cases, this conceptual difficulty arises from the misuse of language. There are actually two different ways to describe many-body state in this situation. In the first quantization language, we basically want to describe the state by asking which particle is in which state. For example, we want to say the first particle, this which is actually the label of the particle, so the index of the particle. We want to go through every particle and say the first particle is in which state, second particle is in which state. We keep asking this kind of question, and then if we answer each of the question, we can write down the state for each particles, and then that forms a sequence of state label that labels the first quantized basis state. So that's our approach. But you can see this approach has an inappropriate language here because we are asking about a specific particle where the particle in identical particle systems are indistinguishable. So that's why we need to change our way of asking questions and labeling the state in second quantization. Second quantization basically means another way of asking this question. So how many particles are there in every state? Which is actually the approach taken here. So instead of taking the particle as our previously, we have n particle, and then we ask what should be the state that I fill into these particles, right? And then now we are asking, we have these different states, and how many particles should I fill into the states? So that's two different ways of thinking about this problem. Here is also the same thing. I have three possible states, and how can I fill my particle into the state? By answering how many states are there in the first, how many particles are there in the first state, in the second state, and in the third state, for example. So that's the idea of changing the language. By changing the language, we will no longer encounter this problem of trying to identify which is the first particle and which is the second particle. For example, if you have a first quantized state like alpha beta, it describes first particle in alpha, second particle in beta. But now in the second quantization language, we basically say that this means that there's one particle in alpha and there's another particle in beta. So in alpha, the occupation number is 1, and the beta single particle state, the occupation number is also 1. We can just use two ones, one for alpha, one for beta. These two 1 labels these states. So both alpha beta state and beta alpha state is a first quantized realization of this kind of one particle in alpha and one particle in beta. So we no longer need to distinguish which one is the first particle, which one is the second particle, because we really cannot tell what do we mean by the first particle. So in this way, the new description does not require the labeling of particle. Therefore, there's no redundancy or unphysical basis state in this new Hilbert space. So that forms a concise and precise description that is both concise and precise. Concise means that it doesn't contain this redundant state, and precise means that it actually describes all possible states within this Hilbert space. Okay. So each basis state now is labeled by the so-called occupation numbers. The occupation number is an integer, actually a natural number, which goes like this. So if you have n particle and trying to occupy d different states, and then you basically need to create another sequence, and this sequence we call it n, which is different from alpha, because alpha is like trying to label the state of each particle, but n is trying to label the occupation number of each state. And then this n is, n1 is the occupation number of the first single particle state, n2 is the occupation number of second single particle state, and so on. And then you can use this sequence of occupation numbers collective together to label a many-body state. And in that way, in that description, there's no redundancy, there's no ambiguity. And there's a rule that for bosons, because there's no constraint on the numbers, number of bosons we can put in one state. So for this single particle state alpha, it can be occupied by n alpha different bosons, and this n alpha goes arbitrarily to infinity, starting from 0, 0, 1, 2, 3, and so on. But for fermions, there's a constraint due to Pauli Exclusion Principle that for any alpha state, the occupation number n alpha can only be either 0, meaning that the state is not occupied by the fermion, or 1 if the state is occupied by the fermion, but it cannot be 2 or higher because you cannot have two fermions occupying the same state alpha. So that is the only constraint. So for bosons, you basically can choose this n. And then there's, of course, in the end, from the very beginning, we want to occupy this system with n particles, right? So there's also a constraint on these numbers, that these numbers are not chosen independently. They should be chosen in a way that the occupation number, if you sum over all possible states, sum over the numbers of bosons in the first state, number of bosons in the second state, and so on, it must be the total number of bosons in the system, which is the capital number n. So given the single particle Hilbert space dimension d, and given the total number of particles in the system, we can enumerate all the possible choice of these little n occupation numbers, and every different choice basically corresponds to a different basis state of this many-body Hilbert space that is denoted as this cat vector with this n sequence, or the occupation number sequence. So these states, they actually serve as a basis in this reduced Hilbert space. They are called the Fock states because they are created by these scientists. And then all the Fock space forms a complete set of bases of the many-body Hilbert space, which is called Fock space. Of course, there are two versions of Fock space. One is the bosonic version, and the other is the fermionic version. But if you don't worry about the details about whether the state is exchange symmetric or anti-symmetric, at a very high level, they can be just called Fock states and Fock space. So with this principle, any generic second quantized many-body state once you specify whether it's a bosonic state or fermionic state, it will be a linear combination of either the bosonic Fock states or the fermionic Fock states, which goes like this, which the state will be taking all these bases and then summing over all the possible patterns or sequence of this occupation number. And for each occupation number, there's a corresponding coefficient, linear superposition coefficient, which is also a complex number in front of it in order to combine them together and form the many-body states. Okay, so that's the idea. So that's a different language, and then we have a different set of bases. So now the goal is to make connection of these basis states to the original state that we construct in the first quantized language. Remember that in the first quantized language, we use this alpha vector, and that is the first quantized language. In the second quantized language, we use this n occupation number. Alpha is talking about every particle in which state. N is talking about every state holds how many particles. So there must be a relation between these two because this n state belongs to this subspace. And then this subspace is a subspace basically means that any state n here, which is a state here, must also be able to be represented as a space in the larger Hilbert space. Because the larger Hilbert space has the representation power to represent any point, any state within this space, right? So the Fock state is a special subset of states which should also be written in terms of this linear combination of alphas. So now our goal is try to understand how do we rewrite this n state in terms of alphas. And that makes a connection between the second quantized language, which is better because it's precise and concise. But although it has this advantage, but at this point, it's not clear how to construct this state. So we need to make this connection because these states we know how to construct. We can start from the single particle state and then use tensor product to construct them. And then if we further know how to linearly combine them to form these states, then we basically has a very solid foundation for all these Fock states. Okay, so that's the idea. So every Fock state has a first quantized representation. That's what we want to talk about. And then first of all, the Fock state where all the occupation number is 0 is very special because you are basically occupying no particle in the system. And then that kind of state is called a vacuum state. And the vacuum state in the second quantized language is denoted by a big 0, which means every occupation number is 0. And then it actually corresponds to, it actually doesn't have an alpha representation. It corresponds to something called the tensor product unit in the first quantization, which can be written as a single one. It's like, it's tensor. So when we talk about tensor product, we say, how do we tensor product two vectors together? But can you imagine that there's an object where you tensor product with any vector, it doesn't change the vector. Usually if you take two vectors, tensor product, you need to expand the second vector and then expand the first vector, copy the second vector so that the result is a larger vector. But imagine that there's a tensor product unit, you can just think of it as a 1-by-1 matrix. So if it is a one component vector, and then the vector component in that one component vector is also 1, so that's why we denote it as 1. So that kind of vector, if you tensor product with any vector, it keeps the vector the same. So that kind of vector is actually considered as the vacuum state. That's very special. We will see why we need to design that later. But okay, then in general, any other non-zero occupation number. So also, you may notice that I put a B or F here. It is because there are two versions of Fock space. One is a bosonic and fermionic. We need to distinguish them. So we will put this B and F to denote whether these correspond to the vacuum state in the bosonic subspace or the vacuum state in the fermionic subspace. But they are actually the same state. So the vacuum state is shared. This vacuum state is shared between the bosonic and fermionic subspace. That's in the intersection of these two subspaces. That is because previously we say that there's no way to distinguish boson from fermion if you only have one particle or zero particle, right? Because the only way to distinguish them is to see whether under exchange the state vector gets a minus sign. But if you only have 0 or 1 particle, there's no way to exchange. you need to have at least 2 particles in order to start to distinguish boson from fermion. So there is a very small subset that is overlapping between these 2 subspaces, which correspond to the vacuum state and the single particle states. Okay, so we can also talk about those non-zero occupation numbers as a single particle, single mode Fock states, which means let's first start from the case where we only have a single mode, which means we have a single particle state. We pick one state. For example, we have these slots, but we only want to focus on this slot, which is labeled by alpha, by this state alpha. And we want to see how many boson or fermion can we build on that. So for example, we can have a system where everywhere else is vacuum. So all the other modes are not occupied, it's 0 everywhere else. But it's only there's n particle occupying that particular alpha state. Of course, I specified the alpha at the very beginning as my starting point. So let's first focus on the single mode problem where we can already talk about many-body states, because we can occupy these modes by either no fermions or 1 fermions. And for bosons, we can occupy it by no boson, 1 boson, 2, and 3, and so on. So, so we will denote this state as this n alpha. And then for the fermionic, if it is only occupied by a single particle, then basically the corresponding first quantized wave function is like this alpha. So this notation means that there's 1 particle occupying the state alpha, and it is in the bosonic subspace. And it turns out that this state is identical to 1 particle occupying the state alpha in the fermionic, one fermion occupying the alpha, 1 boson occupying the alpha. They are the same thing, because there's no difference between boson and fermion if there's only 1 particle. And that state is precisely described by the original state vector of this alpha. There's no need to extend it, basically. It falls back to our previous description of single particle physics. So now, for fermion, you can't go further. You can't have 2 fermions occupying alpha. But for boson, you can continue moving on. You can have 2 bosons occupying alpha. Then the state is like you have a particle in alpha and another particle in alpha. So you need to tensor product them together. And then in the first quantized language, we will interpret this state as the first particle is occupying alpha, and the second particle is also occupying the alpha state. But after symmetrization of this basis, we can see this basis is already symmetrized by itself, because under symmetrization, you need to exchange these labels, but they are labeled by the same label, so under symmetrization, it's still the same state. So it automatically already satisfies the property that it is symmetric under permutation or under exchange, then it qualifies as a bosonic basis state automatically in this case. You don't need further operations to symmetrize it, actually. So the 2 boson state actually is described by this first quantized language. And if you have 3 bosons occupying alpha state, that means you can write it in this way, that the first particle is in alpha, second in alpha, third is also in alpha. But then we don't care about this label of the particle. We don't care which one is the first. So we basically, it's still, after symmetrization, it's still this state. And then you can write n boson occupying alpha, like alpha tensor to the nth power. Because if you have n object multiplied together, right, we can use power to denote n object multiplied together. But now we have n vectors, which needs to be tensored together. Then we can use this notation, tensor to the nth power, to denote that there are n factors being tensored together, okay? So that is the very simple idea of how to convert all these occupation number states into first quantized language. So this is the case, very simple case, that there's only a single mode or a single particle state being occupied. So this mode basically stands for the single particle, stands for the slot, stands for these boxes where you can put particle in the boxes. And then different modes describe different states that the particles can rest in. Okay? We can also have different multi-mode Fock states, meaning that there are at least 2 different modes, for example, alpha and beta, and then you can occupy them by different number of bosons or fermions. For example, if you want to describe there's 1 boson in alpha state, 1 boson in fermion state, then the corresponding state vector is like this, because you need to put alpha beta, but now alpha beta is not beta alpha. If you exchange the labels, they are no longer the same. So that's why in order to make the state bosonic, you will have to symmetrize the state. And by symmetrization, you end up with such a state which is alpha beta plus beta alpha. This plus sign ensures that if you now try to exchange the two labels, the two terms will switch. But the two terms switching doesn't affect the, doesn't make any difference. So that is a bosonic property that is symmetric under permutation or exchange. And for fermions, you need to anti-symmetrize the state, so there's a minus sign. And this minus sign is very crucial because now if you try to exchange the labels of the first factor and the second factor, you basically switch the two terms. But now, because the two terms are combined with a relative minus sign, so switching the two terms leads to an overall minus sign in the front, which means that if you try to exchange two particles in a fermionic state, you will get a minus sign in its state vector, okay? So that's the idea to construct like a multi-mode this Fock state. And we can further extend this idea. For example, here are some more examples. Suppose we have a bosonic state, then we can actually occupy a mode with more than one bosons. We have two bosons occupying alpha, one boson occupying beta. Then that means we have two bosons occupying alpha. So alpha will be repeated twice, and then one boson occupying beta. Then beta will only appear once. And then you need to tensor product them together to form the many-body state. But then, because we know that the boson state must be symmetrized, so you need to symmetrize them by permutation of all the labels, such that in this way, only in this way, you remove the distinction of these particles. Because if you only keep the first state, if there's only the first term, that means you can actually distinguish, tell what is the first boson, second boson, and third boson, but that's not the case. So, for example, this beta state can appear either in the third places or second or the first. So either the first boson or the second boson or the third boson can be in the beta state. There's no way to tell which one is the beta state, which boson is in the beta state, because all these bosons are all on equal footing, they are all equivalent. So all we can say is that in the system, there's only two alpha there are only two bosons in the alpha state and one boson in the beta state. So you need to summing over all the possibilities that satisfy these occupation number constraints, and then every possibility will appear with equal probability. So, so that's why the state vector wave amplitude are the same, 1 over square root 3, because this 1 over square root 3, if you square it, that's a probability. And then all these different cases have the same probability, so you can't really distinguish which one is which one. And then that leads to this bosonic basis. So we can see it's very simple that you basically need to convert these numbers into alpha to the second power and beta tensor to the first power. And then you only need to first write down the first term. You just need to write down the first term. And then you apply the symmetrization operation on this first term, automatically generates all the remaining terms. And then the symmetrization operation also take care about this plus or minus sign in combining these terms automatically. And then after that, you normalize the state a little bit to find the normalization factor in the front. And then you can translate this occupation number or the Fock state into the first quantized, the second quantized language into the first quantized language. And using the same principle, we can write down a fermionic state, which we have one particle in alpha, one particle in beta, one in gamma. So you first write down the first term that corresponds really to one particle in alpha, one in beta, and one in gamma. In that case, you don't care about, okay, I need to label which one is the first one, because you know you will do an anti-symmetrization later to remove this labeling of the particles, so to make them identical. So first of all, you just assume that the first fermion is in alpha, second fermion is in beta, third fermion is in gamma, but then you anti-symmetrize everything by enumerating all the possibilities. And then while anti-symmetrizing, you need to make sure that when you have even number of permutation exchange, I mean the permutation sign is even, or there's even number of exchange, you don't need to attach any sign. But if there's odd number of exchange, then you need to attach a relative minus sign. For example, if you start from this state to the last state, What happens is that alpha doesn't change, but you are permuting beta and gamma label. Permuting the label of the second and third particle, then this is a single exchange. Single exchange will give you a minus sign. So that's why there is these signs, okay? So there are altogether 6 terms. 3 of them have the same sign, and 3 of them has the opposite sign compared to the first one, okay? So altogether 6 of them, each one has a 1/6 probability, and then so that's why the normalization factor is 1/√6, because the wave amplitude is the square root of the probability. So in this case, we have equal probability to see any one of these, and then with the correct fermion minus sign that take care of these properties, okay? Fermionic state properties.
Professor,
yes?
the signs you are giving is because how many permutations you make? So
Yeah.
Odd number, then it's minus, even number, plus?
Yeah, for example, let's explain why this is plus. Because in order to start from this state, you always take the first state as a reference state, as the starting point. And then you use the first state to determine what should be the sign in the second, third, not first state, I mean first term, to determine what are the remaining term, how are their sign in front of that is relative to this first term. Because the overall sign doesn't matter, only this relative sign matters. So if you want to determine what should be the phase factor difference between the second term and the first term, you need to count. If I want to start from the first term and go to the second term by permutation, how many times of exchange should I do? I need to first change this alpha to here, and then to here, in order for the beta gamma to appear in the front and alpha push to the end, right? So by doing this exchange, I get a minus sign. Doing this exchange, I get another minus sign. And then there are 2 exchanges, 2 minus sign goes to a plus sign. What about this one? This one is like, I need to start from here to here, then I need to push this alpha to here, and then I end up with here. So that's only 1 exchange. And then because there's only 1 exchange, then 1 exchange is a minus sign. And then, for example, this one, I need to first push alpha to the end, and then I need 2 exchange. But then I also need to exchange beta and gamma. I need another exchange. So in order to start from here to there, you need 3 exchange. 3 exchange is also an odd number of exchange, so there's a minus sign. So the sign only depends on whether it's an even number of exchange or odd number exchange when you go from the first AI. Because it doesn't matter if I put the overall phase factor in the front, then the phase factor distributes into every term.
Are the number of exchanges for each relative to the very first?
Oh, you can also take this one as the reference state. You will end up with the same result. So you don't need to take the first one as the reference state. You can take any one of them, because all these sign is only a relative concept. It's saying that this configuration and this state basis and this basis has a relative minus sign, and these 2 bases has a relative same sign. And actually, these 2 bases, if you take these 2 bases, they have relative the same sign, because they are both of them are relative minus to the first one, so they have relative the same sign. And then the relative sign is the only thing that matters. And you may worry that if I take different reference state, I end up with different results. But there is a mathematical theorem that ensures there's no such inconsistency. This is the nice property of permutation group, because the way that we design this sign structure, we can see it's not arbitrary. It's counting the number of exchange and depending on the parity of the exchange. For example, I didn't count the number of 3-fold permutation, and depending on the parity of that. Why don't I do that? The reason is that only counting the exchange, the parity of exchange, forms a mathematically consistent one-dimensional representation for permutation group. That's a lot of jargon, but basically that means that's a consistent representation such that any permutation group element can be nicely represented in it, and it doesn't violate the permutation group multiplication rules. Yeah.
Another question. The first term you have there with the minus sign, I think you said you make three exchanges, but I was thinking just maybe only 1. Why do you say 3 instead of 1?
This is 3 exchange. Because you need to first take alpha through beta through gamma, these 2 exchange, and then you need to exchange beta and gamma.
Okay, so exchanges must be between states that are like 1 step far from each other. They have to be together to make the permutation.
That's also fine. You can you can also exchange alpha and gamma, right?
Yes.
That's also okay. So that's also a minus sign. The fact that you can, so I propose alpha, beta, gamma. First exchange alpha and beta, and then exchange alpha and gamma, and then exchange beta and gamma here. So the exchange basically forms a pattern, forms a path. But this path is equal to this one with a straight line, alpha, beta, gamma, right? It's like, because if you look from far, right, this line actually doesn't change, although the wing winds around, but it actually, if you straighten it, it's a straight line. What actually gets exchanged is this alpha and gamma. So this configuration and this configuration, this approach and this approach, they are talking about the same permutation. And this approach has an odd sign, and this approach also has an odd sign. That's the idea. That's also the internal consistency in this permutation representation, that no matter you count it as 3 permutation or 1 permutation, it doesn't change your answer because 3 and 1 are both odd number. You will never find a case where 3 permutation can be reduced to 2 permutation. That's impossible. But you can reduce 3 permutation into 1 permutation, or you can even expand 3 permutation to 5 permutation. For example, I'm not very clever, so I do another 2 permutation here, right? I can do something like that. So then there will be 5 permutation there. Then by counting that, that's also fine. That's also a minus sign. So there's a lot of freedom to count the number of exchange. By decomposing a permutation into number of exchange, there's an infinite number of ways of doing that. No matter which way you take, the parity of exchange will never change. And the sign only care about the parity of the number of exchange, not the number of exchange. You can make a different counting about number of exchange, but you never get wrong about this parity. So that's the idea. Okay? So, okay, with those discussions, I think I can conclude that today's discussion, basically we establish how to represent the second quantized in terms of particle number occupation basis. We can write down this basis in the bosonic space and fermionic space, which corresponds to this occupation basis. You can see labeled by occupation numbers. So in general, if I have a bosonic state which are labeled by occupation numbers, where every state alpha gets occupied by n alpha state, what we need to do is we first take the first alpha and then copy it n times, tensor them together, and then take the second possible alpha, which maybe here is labeled by beta. So this alpha will go through all the mode labels. So this alpha will go through all the mode labels, like go through 1, 2, 3, 4, and so on, all the way to D. And then for every one, you basically need to tensor it by the occupation number and tensor everything together. So this will be basically n, actually a lot of factors. I think in total n factors tensor together. So all these expressions basically correspond to the first term. For example, this first term is like alpha to the first power, beta to the first power, and gamma to the first power, like that. And then once you write down this first term, you can use a symmetrization operation to symmetrize the term. And after symmetrization, and then, of course, you also need to take care of the normalization, but I don't want to derive this normalization factor here. You just believe in me that this normalization factor is automatically calculated in this way, such that the scalar product of this basis is 1, basically. The normalization is determined that way. And then for fermionic state, you also write down the first term, and then use the anti-symmetrization operation, and then followed by a normalization. Well, the symmetrization basically means that you apply the permutation operator to the state, and then by applying that, meaning that you pick a permutation in the permutation group, and then apply that permutation to the state labels such that it becomes a different state, and then you're summing over all the possible permutations. That is symmetrization. Anti-symmetrization is you still summing over all the possible permutation of this first term, but every time if your permutation contains odd number of exchanges, you need to put a minus sign in the front. and then summing over all of them, that is anti-symmetrization. So in general, fermion and boson state can be very generically constructed from this first quantization language using these formulas. So that's it for today. Thank you.